In module 2 of chapter 10, we have discussed the phenomena of dispersion. In module 1 of the same chapter, we have discussed about the nonlinear wave equation, and we find that the nonlinearity and the dispersion play a fundamental role to find the water wave motion. If we consider nonlinear shallow water wave equation, then it leads to the breaking phenomena if we do not consider dispersion. But this breaking can be prevented if we can incorporate the dispersion effect. Therefore, the effect of nonlinearity and dispersion is important to explain some physical phenomena. With this purpose, in module 3 of chapter 10, we shall discuss about the nonlinear KdV equation, where both the nonlinearity and the dispersion effect are considered. We have considered KdV equation because this equation arises in many physical problems such as plasma waves, magnetohydrodynamics waves, and the wave with long wavelengths. Therefore, we divide the entire module into some subsections. In section 1, we shall first introduce the KdV equation. Then we shall solve this equation assuming travelling wave solution. Finally, we shall give or tell about the conservation property of KdV equation. Now, we are going to the slide show of this module. First, I shall introduce KdV equation, which is the short form of Korteweg-de Vries equation. First, we shall start with the dispersion relation for water waves in an ocean of depth h0, which is given by omega 0 equals to Gk tan hyperbolic k h0, where h0 is the depth of the ocean, omega is the frequency of the wave, and k is the wave number. So, from that equation, we can find the value of omega as function of k as Gk into tan hyperbolic k h0 to the power half. Now, if we expand this function, we will get omega is equivalent to C0k into 1 minus 1 by 6 k square h0 square, where C0 equals to Gh0 to the power half, and this denotes the wave speed. In many physical problems, wave motion with small dispersion exhibits such k cube term, whereas in case of non-dispersive wave, omega is only C0 into k. Now, the equation for free surface elevation, which is denoted by the variable eta and which is function of x and t, is given by del eta del t plus C0 del eta del x plus sigma del cube d eta del x cube equals to 0, where sigma is defined as sigma equals to 1 by 6 C0 H0 square, and this is a constant for fairly long waves. The equation 2 is known as linearized KdV equation for fair long waves, and this wave is propagating along the positive direction of x axis. Now, in this equation, the phase velocity Cp is defined as omega by k and its value is C0 minus sigma k square. On the other hand, the group velocity of the wave train, which is denoted by Cg and which is defined as d omega dk, is equals to C0 minus 3 sigma k square. And these definitions are given in equation 3. From equation 3, it can be noted that value of the phase velocity is greater than value of the group velocity, and the dispersion arises due to the term k cube in the dispersion relation 1. Now, if k going to 0, that means if we consider a long wavelength wave, then from equation 3 we get Cp equals to C0 and Cg equals to C0. That means the values of the phase velocity and the group velocity becomes constant, and this is the characteristic of a non-dispersive wave. Therefore, for long wavelength the equation becomes to a non-dispersive wave. In 1895, KdV derived the nonlinear equation for long waves in a channel of depth h0, and that nonlinear equation is given by del eta del t plus C0 into 1 plus 3 by 2 eta by h0 del eta del x plus sigma del cube eta del x cube equals to 0. And in this equation you can see the nonlinear term, which is here 3 eta C0 divided by 2 H0 into del eta del x. And the KdV equation, I have already told, it arises in many physical problems like water waves in long wavelengths, plasma waves and magneto-hydrodynamic waves, etc. Now, I want to find travelling wave solution of the nonlinear KdV equation, which is written in equation number 4. So, for that we assume the elevation eta as in the form h0 into fx, where x equals to x small x minus ut, where u denotes the velocity of the wave and f is an arbitrary function, and we want to find the functional form of f. Now, we substitute 5 into equation 4, that means into the nonlinear KdV equation, and we get 1 by 6 h0 square f triple dash plus 3 by 2 f dash plus 1 minus u by C0 f dash equals to 0, where f dash denotes derivative of f with respect to capital X. Now, since we are going to find the expression for small f, we integrate the previous relation, and after integrating we get 1 by 6 h0 square f double dash plus 3 by 4 f square plus 1 minus u by C0 f equals to a, where a is the integrating constant. Again this equation can be integrated. So, for that we multiply this equation both sides by f dash and then we integrate and obtain equation 6, where b is the another integrating constant. Now, let us think about the solitary wave solution, that means the quantity f, f dash, f double dash all goes to 0 as mod x tends to infinity. and we think about that particular solution for which capital A equals to 0 and capital B equals to 0. So, under this condition equation 6 reduces to, so in equation 6 we put A equals to 0 and B equals to 0. So, it reduces to 1/3 H0 square f dash square plus f square into f minus alpha equals to 0, where alpha is a constant equals to 2 into u by C0 minus 1. Then we obtain the value of f dash from equation 7. So, it find value of f dash square first, this equals to 3 by H0 square f square into alpha minus f. Then we take the square root of f dash and then we integrate. So, we obtain x minus x0 equals to H0 square by 3 square root into integration 0 to f df by f into square root alpha minus f. Now, to find the value of this integral, we substitute f equals to alpha sec h square theta. So, if you substitute that, the value of the integral can be obtained easily. So, after integration it becomes x minus x0 equals to 4 H0 square by 3 alpha to the power half into theta. So, the value of f, so if we go back to the previous slide, what is f? So, we obtain the value of f from here, f equals to alpha into sec h square theta. So, fx equals to alpha into sec h square, this is the value of theta which is written in the square bracket, and the final solution, that means the value of eta, there is a relation between eta and f. This is the relation which is written in equation number 5, eta equals to H0 into fx. So, expression for eta becomes eta 0 into sec hyperbolic square into 3 eta 0 by 4 H0 cube to the power half into x minus ut, where eta 0 is defined as alpha into H0. So, equation 9 gives the solution of the nonlinear KdV equation, and this solution is called solitary wave solution or soliton. So, if you observe the solution, you can see that this represent a single hump. So, if we plot the solution, so this represent a single hump about x equals to 0, capital X equals to 0, and the amplitude becomes 0, that means eta becomes 0 as mod x tends to plus infinity or minus infinity, and these humps goes in the right direction of small x axis with velocity u, and the value of u can be determined from this relation. In the middle of the slide you can see that alpha equals to 2 into u by C0 minus 1. So, from this relation you can find the value of u, and this u gives the velocity of the soliton. So, u equals to 1 plus alpha by 2 into C0. So, here you can get the value of the u equals to C0 into 1 plus alpha by 2, and you know the value of alpha. So, if you substitute, you get u equals to C0 1 plus eta 0 by 2 H0. It is to be noted that the velocity of the wave depends on eta 0, or in other words velocity is proportional to eta 0. Therefore, the taller soliton moves with more velocity than the shorter solution or soliton, and the width of the soliton, which you can obtain from this. So, width of the soliton is 3 eta 0 by 4 h cube to the power minus half. That means, therefore, the width of the soliton is inversely proportional to eta 0. So, a taller wave have narrower width. Therefore, taller solitons moves faster and are narrower than the shorter ones, and they can overtake the shorter one and can emerge from the interaction without change of shape. And this is one of the characteristic of solitons, and these solitons interactions show that the solitons behave like elementary particles, and these phenomena can be observed only in KdV equation. So, the earlier one was some particular solution. Now, I am going to obtain a general solution of the equation. So, if we go back to equation 6, so in this equation, in the first case we assume that particular solution for which A equals to 0, B equals to 0. Now, we are not assuming A, B as 0, but we are thinking about a bounded solution and which oscillates between 0 and alpha. So, we are seeking a real bounded solution. So, for that f dash square must be greater than equals to 0, and it varies monotonically until f dash equals to 0, and it has, you can see this is a cubic equation in f. So, it has 3 roots. Since we are thinking about the real solution, so these 3 roots must be real, and we are also interested to find, I have already told, the oscillatory solution which oscillates between 0 and alpha. So, without any loss of generality, we choose f1 as 0 and f2 as alpha, and the third 0 must be a negative number. So, we put that f3 is equals to alpha minus beta, which is a negative number. So, 0 less than alpha less than beta. Thus, from equation 11 we obtain 1/3 h0 square f dash square equals to f into alpha minus f into alpha minus f minus alpha plus beta. Taking square root both sides, we obtain equation 12, where capital U is the velocity of the wave, which is given by the relation which you can see in the slide. Now, to find the value of this integral, we put alpha minus f as alpha into q square. Now, we are changing the variable from f to the variable q. So, with this substitution, the integral in the right hand side becomes dq by 1 minus q square into 1 minus m square q square whole to the power half, where m is equal to alpha by beta to the power half, and this is the famous elliptic integral. So, its solution can be written in terms of Jacobian sine function. So, q equals to Sn of 3 beta by 4 h0 square to the power half into x m, where m denotes the modulus of the Jacobian elliptic function Sn Zm. Therefore, f, the value of f, which is from this equation f equals to alpha into 1 minus q square. So, if we substitute that alpha into 1 minus q square, we obtain the value of f which is written in equation 14. So, the solution is now in terms of cosine function, elliptic cosine function, and this Cn(Zm) is called the Jacobian elliptic function and it is of modulus m, where we have used the relation Cn square z equals to 1 minus Sn square z. It is to be noted that this Cn function is a periodic function. Since Cn is periodic, Fx becomes periodic. Therefore, the solution of the KdV equation becomes periodic and the period P can be obtained from equation 13. From here, we can find the value of the period as P equals to, which is written here in equation number 15. Let that period equals to lambda, where Km is the complete elliptic integral of first kind and which is defined as Km equals to integration 0 to pi by 2 1 minus m sin square theta to the power minus half d theta. So, therefore, the general solution of the KdV equation represent a train of periodic waves in shallow water, and the solution represent a nonlinear wave whose shape and wavelength depend on the amplitude of the wave. So, if you draw the picture, you can see, and this wave is called nodal wave. This is periodic in nature, and this type of wave can be observed in river with small modulation of amplitude. Now, I shall discuss two particular cases of the general solution. If you take m going to 1, that means alpha goes to beta or alpha is equals to beta, then the Cn(z) function becomes sec hyperbolic z function, and the nodal wave solution 14, it represents the classical solitary wave with wavelength lambda and which approaches infinity due to this property k1 equals to infinity and k0 equals to pi by 2. And if we take the second particular case, if we take m goes to 0, then this Sn(z) goes to sine function and Cn(z) goes to cos function, it becomes cos function, and the solution becomes x equals to, the solution can be written in terms of sine function and cosine function, and with this substitution k equals to square root 3 beta by h0, that means beta equals to this transform the value of fx as alpha by 2 into 1 plus cos kx minus omega t. So, this is nothing but the solution of linearized KdV equation, where omega equals to E into k, and this is the dispersion relation for the small amplitude wave equation, and from this dispersion relation you can find that these first two terms are similar to the first two terms of the dispersion relation in water wave problem. In this section, I shall discuss about conservative properties of KdV equation. The KdV equation itself is in conservative form. In late 1960s, Miura et al. Discovered that there are infinite number of integral of motion for KdV equation, and it forms completely integrable Hamiltonian system, and this integral of motion corresponds to conservation of mass, momentum energy, etc. In this section, I shall discuss about two conservation of mass and energy. Now, we are going to the slide presentation. An equation is said to be in conservative form if it can be written in the form which is given in equation number 17. That means, if it can be written as del t plus del x equals to 0, where capital T is called the density and capital X is called the flask. Assuming that T and X are integrable in the interval minus infinity to plus infinity, and if you assume that capital X tends to 0 as mod x tends to infinity, then integrating equation 17 with respect to x over the interval minus infinity to plus infinity, we get d dt of integration minus infinity to plus infinity t dx equals to value of x at minus infinity to plus infinity. So, it is 0. Therefore, we get integration of capital T dx equals to constant. Thus, the density is conserved. Now, we shall go back to the nonlinear KdV equation, which is given by del u del t minus 6 u del u del x plus del 3 u del x cube equals to 0. This is the standard equation, standard form of the equation. Now, this equation can be written in the form del u del t plus del t of minus 3 u square plus del 2 u del x square equals to 0, where capital T is equal to small u and capital X can be assumed as minus 3 u square plus del 2 u del x square. Now, if we integrate this equation with respect to x over the interval minus infinity to plus infinity, that means over the whole real axis, we get d dt of integration u dx equals to 0 or integration of u dx equals to constant. So, the integral in the left hand side represent the total mass of the system. Therefore, this integral of motion represent the conservation of mass. Now, to get the another integral of motion, we multiply the KdV equation, that means the first equation of this slide, by u. Then we can write the terms in this way as del t of half u square plus del x of minus 2 u cube plus u del x minus half del u del x whole square equals to 0. Now, if we again integrate this equation with respect to x over the whole real line, we get d dt of integration u square by 2 dx equals to 0, or in other words, integration of u square by 2 dx equals to constant. So, these represent the conservation of energy. So, in this way one can prove the other integral of motion or the other conservative properties of the KdV equation. Therefore, in module 3 of chapter 10, we have discussed about KdV equation. The solution of nonlinear KdV equation is a solitary wave, which is a new phenomena, and this is the outcome of dispersion and nonlinearity. Now, we end this module.